let's have a look at electron configuration and how to diagrammatically represent the electron configuration for atoms. To do this, we need a little bit of history. So Niels Bohr proposed that electrons exist at discrete energy levels, and he came up with this through a variety of experiments. He said that they were not necessarily circular. He designated these energy levels with the symbol N, and he said that we have energy level 1, 2, 3, 4 and 5, and the lowest energy level, number 1, was closest to the nucleus. What he found in his experiments, and what he proposed based on that, was that electrons can jump from a lower energy level to a higher energy level by absorbing a definite or discrete amount of energy. He got this from observing what happens when an electron jumps from a higher level, so let's say from level number 3 down to level number 1, and a photon of light of a discrete colour was given out. He based this on the hydrogen atom. So, the quantum mechanical model says it's not possible to determine the location of electrons, but it is possible to predict a region of probability which we call an orbital. And those orbitals exist within the energy levels, or what we call shells of electrons. So there are some numbers that we need to have a look at, or some definitions. First of all, we've got what's called quantum numbers. And N, as we said before, represents the shell or the energy level within an atom. We've also got N squared, so if we square whatever energy level it is that we're talking about, it gives us the maximum number of orbitals for a shell. We've also got types of orbitals, and they increase in complexity. So our S is a spherical shape, P is a dumbbell shape, and we get to much more complex orbitals after that. And it's a region of probability that an electron will exist in. So let's have a look at a chart of how these things are put together. So on the far left-hand side, I've got my energy level or shell. The next column tells me how many subshells there are or orbitals there are. The third one tells me the type, so whether it's S, P, D, F. The fourth one tells me the maximum number of orbitals for that particular shell. The second last column gives me the total number of orbitals, and that comes from N squared, this number up here. And then finally, what we have is the total number of electrons that are possible in that particular energy level. And that's given by the formula 2n squared, where n is our energy level. So for energy level number 1, we can have one type of sub-level or orbital. And this particular type of orbital will be an s orbital. So we have a maximum of one orbital only from the s, and this gives us a total number of one orbital. N squared is the 1. We also, if we do our 2n squared, it gives us a maximum number of electrons for the first energy level of 2 from the 2n squared. If we go to our second energy level, we can have two types of orbitals, and this is our s and our p from the ones above. And the reason that it exists like this is because you can't have multiple s orbitals within the one energy level. So the number of orbitals will be 1 for the s, and this time we have 3 for our p's. And this gives us a total of n squared, which is 4. So we've got the 1 plus 3 gives us 4 orbitals. And then if we look for the total number of electrons possible within this second energy level, 2n squared gives us 8. For level number 3, we've got three types of orbitals, S, P, D, F. They can all have the S can have 1 orbital, the P's can have 3, the D's can now have 5, which gives us a total of 9 orbitals, or n squared of 3, 9 orbitals in total. And this allows us to have a maximum of 18 electrons in that particular energy level. Finally, we've got our fourth level, 4 types of orbitals or sub-levels. The S type, the P type, the D type, and this time the F type. We get n squared, which gives us 16 maximum orbitals. We'll get 1 from the S type, 3 from the P's, 5 from the D's, and 7 from the F orbital types. which gives us a total possible of 32 electrons in the fourth energy level or fourth shell. So how do we go about determining electron configuration? Well, we have our shells, 1, 2, 3, 4, or energy levels. We've also got our orbitals. So for the first level, we've only got our s orbitals. For the second level, or the second shell, we've got the s's and the p's. For our third level, we've got s, p's, and d's. And for the fourth level, we've got our s's, so 4s. The 4 denotes the energy level. The p's, so 4 p's, 4 d's, and 4 f's. Now, one thing that you'll notice is that our order, we would think, goes SP and then the 3D. But in actual fact, in terms of the amount of energy that it requires to get into these orbitals, the fourth level, so the shell number 4 s orbitals, have slightly lower energy than the d orbitals. So they come first. And that's important when we determine our configuration a little bit later. So let's look at some rules to show the configuration of atoms. First of all, we place electrons by starting with the lowest energy shell, n equals 1. And the electrons will go into the s orbital in preference to the p's and the d's and the f's. Secondly, we can place a maximum of 2 electrons per orbital. And that comes from what's called the Pauli exclusion principle. We don't need to go into the detail here. Let's take 4 examples. So we've got oxygen with an atomic number of 8. If we draw the shell structure for oxygen, there's 2 electrons in the first shell, 6 electrons in the second. In order for us to draw the electron configuration now, we follow this procedure. So we have 1s, maximum of 2 electrons in the 1s shell, 1s orbital. Then we move on to the 2s. So we get 2 electrons again. So we go 1s2, 2s2, and the next one up is the p's. So we can only have 1 orbital there, 1 orbital there. Our p's we can have 3. Hence, we can actually fit a maximum of 6 electrons. 3 orbitals times our 2 electrons per orbital gives us 6 possible electrons. So for oxygen, we've got 1s2 from the first shell, 2s2, our second s orbital, and then we've got 4 electrons left. 2 plus 2 plus 4 gives us our 8 for a neutrally charged atom, or what we call a ground state atom. So our electron structure, or electronic structure for oxygen, 1s2, 2s2, 2p4. Magnesium with an atomic number of 12, a shell structure of 282. Remember, the second level can only have 8 electrons maximum. So we get 1s2, 2s2, 2p6, get to here now. Then we go to 3s2, and s's can hold a maximum of 2 electrons, so we can put the last 2 in there. So in total we've got 2 plus 2 plus 6 gives us 10, plus 2 gives us 12, which is the number of electrons that we have in a neutrally charged atom. Our third example, we've got argon, atomic number 18, 288 for our shell structure. And it's 1s2, 2s2, 2p6, 3s2. And now we go to 3p, 6 possible electrons here. If we count up the number of electrons, 2, 4, 10, 12, 18 altogether here. So this is our electronic structure for argon. And our final example is calcium with an atomic number of 20 and a shell structure of 2882. So we get 1s2, 2s2, 2p6, 3s2, 3p6 up to here. And then we should go into 3D because that's the third shell. However, as we said before, the 4s orbitals are lower in energy than the 3D orbitals. So we fill the 4s first. Hence why we've got 2 electrons in the 4s shell. Now it starts to get very long from number 20 onwards. So we have a shorthand mechanism where we look for the noble gas structure below the element that we're talking about. We put that into brackets because if we have a look, we've got identical structures here. So we can represent this as argon in a shorthand form, and then whatever else comes after argon in our electronic structure to represent the element that we're looking for. So we get argon in brackets 4s2.